when we talk about molecular dynamics, this is a set of terms that I gave you yesterday that you apply to a molecular structure. After you draw out the Lewis structure, geometry, that you'll learn about in a few minutes, you look at it and you say, okay, what is his chemistry like in that structure? And we found that the items that you need to take into account is electronegativity, bond polarities, I forgot how I put them together, but anyway, bond polarity, molecular polarity, we'll look at that in a minute. Bond strength, that's the one I was forgetting. That goes. Which is proportional to electronegative differences. In that context. And then one that I haven't mentioned is resonance. And finally, molecular geometry. So if you're given a structure what is its chemistry? Well, by going down these terms and knowing what they involve, you go through and look at the bonding structures in these, and you can tell which is reactive for certain issues, situations, and what is non-reactive. Carbon-carbon would be a very strong bond and not very reactive. Same way with carbon-hydrogens. These are poor reactivities because they have low electronegative differences. I showed you that Pauling electronegativity trends yesterday, and it's in that handout that I gave you. The difference between the two elements, the electronegativities of the two elements, gives you an indication whether it's covalent or polar covalent or even ionic. And the more more covalent it is, the stronger the bond. So that because this would be an even distribution of electron cloud around it, and that would give you a lot of density of electrons between the two nuclei. And I call it, as you remember yesterday, I called it electron glue. So the greater the electron density in here, or glue, the stronger the bond. Well, if you get over here and look at this, you see that this is highly electronegative in the periodic table. Remember what we showed you in the trends. As you go right in this direction, electronegativity increases. So when we look at what is bonded to carbon, low electronegativity, to a high electronegativity, then we see that this is a very polar bond and is very reactive. And we describe that in terms of bond strength. The more polar it is, the easier it is to break. Now, I sent everybody a little note last night to clarify what I'm talking about in the reactivity of molecules. Something that will form a stronger bond will replace something that has a weaker bond. For example, if you have an alcohol, some kind of R group attached, well, bonding, oxygen will bond to carbon in this structure a lot faster and with more stability than will chlorine in that structure. So this fragment will go in here and knock this chloride out. The high electronegatives will always leaving groups. And so this fancy molecule will come out and you'll have this OH group, and this is more stable than that because that's a stronger bond. And so what I'm trying to teach you here is that in the molecular dynamics, you look and you see something that has a high electronegative difference. What about the polarity? It's highly polar toward the chloride. We'll talk about molecular polarity in a minute, and I'll show you what that is. But it weakens the bond and makes it labile or reactive, is what it's called, to something else forming a stronger bond. And so by going down this systematically, you can make a decision about the chemistry of some weird looking molecule. You don't have to know what it is, but if you can draw out the structure, you can see pieces and parts, and that will give you some indication of what its chemistry is. Resonance is kind of self-descriptive in that, let me make this a larger screen, in that it is a delocalization of electrons. Across structure of molecule. You'll find resonance in systems that have multiple bonds only. I can just expand it. Double bonds and or triple bonds. If everything's single bonds, it's said to be saturated, is what it's called. And you don't have resonance with that. But structures like this demonstrate resonance. And these double bonds, one of the bonds in the double bond is a cloud that's above and below the structure of that fragment. From a sideways point of view, you'll see this. Like this, maybe the nitrogen would do that. We'll show you this in a little bit. But one of this bond and this bond, which I'm showing here, and well, I lost a bond, didn't I? No, I got it there. I'm sorry. Yeah, I got it right there, and I'm showing the other one here. Actually, that distributes itself over that entire structure. So you have this cloud that builds around all of those elements in there and creates what we call a delocalization of cloud. And this will make more sense after I go through one of the theories on geometry. But what it does, it creates multiple bond sites. Because this entire structure all the way around is negatively charged. So you've got this cloud that kind of goes through all over 4 elements and is negatively charged all the way around this portion of the structure. So if you have some positive thing looking for a home to hook onto, it could hook up any one of those elements. That's the point. And makes a new molecule. And so if you were reacting, what you would get is a mixture of molecules with this positive whatever coming in and attached to different places. Okay, you couldn't isolate one or the other in the reactivity. That's what resonance is, because it smears the electron cloud over the entire molecule it will create multiple sites that a system can bond. Probably the most famous of this is benzene. When we talk about benzene, we're talking about a molecule C6H6. That's a structure that looks like this. I'll just draw it out. It's a ring structure. Cyclohexatriene is what it is. And has a hydrogen associated with each one of these carbons. Like that. Now that's one way to draw it. Or I can draw this way. Double, single, double, like that, and with the hydrogens positioned like this. And the problem is, neither one of those is the actual true structure. These are resonance structures, resonance contributions to what we call a net structure. And that net structure, the double bond, as I showed you in the previous example, would smear over the entire molecule. And so whatever positives you throw at it, it will hook on anywhere in this. And so you have substituent groups, you have multiple mixtures. And so one way to draw this is looking at it from the side. These are covalent bonds in the structure, and these are carbons here, 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 and here, and here. And so you have a halo above the ring, and you have a halo going on below the ring. That's the ring structure of benzene, and of course you could have some kind of substituent groups and so what have you. But the point is, this is delocalized electrons, and accounts for the resonance structure of benzene. One of the characteristics of resonance structures, you always have to have this. All resonance structures must have, let me put must have, alternating single double bond system fragments. In the molecule. So if it has this alternating single double bond structure, you can draw various electron dot structures. One of the structural formulas that's used, say, for something like this, like that, can be written as a structure like this. Those are the same thing, where all the bends and ends are carbons. Now, carbon has 4 bond sites. It's valence of 4, so it'll hook up with 4 things. So you're limited to 8 electrons undergoing bonding. So if you have a double bond here, then you're limited to 2 hydrogens. So 2, 4, 6, 8. Here you're limited to 2 hydrogens, and 2 bonds, really. 2, 4, 6, 8. Here, another hydrogen, and here, hydrogen. So wherever the ends and bends are carbons, then you fill them in with hydrogens. if there's a substituent group that goes into a structure like this, say methyl group, it'll put it in as a group like that. But I'm trying to show you some of the techniques and symbologies that are used in this type of chemistry. One of the final notes in resonance is if a molecule has more than one Lewis dot structure, or more than one Lewis dot structure can be drawn, then it has resonance. For example, SO2, sulfur dioxide. Sulfur dioxide can be written, like this, or it can be written with a double bond on the other side here. Neither one of them are said to be the absolute correct structures, because these are resonance structures. This bond, one of those bonds, distributes, it's delocalized. So the combination of these is your net structure. You have the covalent, you'll always have at least a covalent, but you'll have this cloud that will surround the entire molecule. So one of the questions on exams, if more than one Lewis dot structure can be drawn for a given molecule, it is, and then A, B, C, D, you pick resonance, because you have multiple structures that can be drawn. Now, if you're going on to organic chemistry, you're going to be eaten up by this, because it's a major topic in that. And the best reference that I've ever found on explaining resonance structures at that level, and these are just definitions that I'm giving you, is what we call Daniels, Weeks, pushing electrons. This is a rather small pamphlet-like booklet. It's a workbook, but if you're going to organic chemistry, you cannot go wrong by reviewing this book. It is a workbook and has removable pages, so if you do decide to get one of these, get a new one, so that if you might have used one, probably got pages missing. So you want to be cautious if you decide to do that. But resonance can destroy a student faster than just about anything in organic chemistry, and because it's really a nebulous topic, and it takes a little bit of effort to understand how its reactivity occurs in different organic molecules. But this does a great job in explaining it. So if, just as a word of advice, pick that one up, review it, and it'll certainly help you through the early days of organic chemistry. Across the entire molecule, it creates multiple bond sites in the chemical reaction. Because you have this negative charge smeared over the entire molecule. Resonance generates multiple dot structures or Lewis structures. and by definition, if multiple resonant Lewis structures can be drawn for a molecule, like I did with the SO2, it demonstrates resonance. These are the three main notations you need to keep in mind as you go into the exam. I'm not going to ask you to write out a bunch of resonance structures for molecules. Oh, and resonance structures must have alternating single-double bonds or multiple bonds alternating. That can be a single, double bond alternating, or it can be a triple bond. That would have an extra bond there, or triple bond alternating, and so forth. So these are more factoids about what resonance is and what it can do than the reactive structures that I would, if you were in organic chemistry, I would require you to draw. And so this will answer all the questions on the exam that you need if you know those points. So